I am going to change your guys' quiz dates. So we're not going to do the quiz on Thursday. We're going to spend Thursday doing the rest of curve sketching. When we come in on Monday, we'll do our one question of curve sketching quiz, and then we'll do review, and then we'll still have the unit test on Tuesday. But it's just going to give us a little more time to practice this curve sketching. All right, so lesson 5, a procedure for curve sketching. So this is very important because even if we take a bunch of points like this graph here and we dot them, we could play connect the dots here, but without more information, I don't know if something else is happening. So it could be that I connect the dots and it looks like this graph A here, but it could also look like graph B here. Maybe I have asymptotes and I have something else happening on either side. So if we put all of our knowledge that we've been doing for the last 3 weeks together, we can do these curve sketching procedures. We can't rely solely on plotting points anymore like we used to back in the good old days, because we could be missing critical information. Maybe we didn't get the exact maximum or the exact minimum when we were finding those points. So there's 8 steps to doing curve sketching. So you always start with finding your domain. So remember, it could be that we have a rational expression or a rational function. So maybe we have A over B, so where B is not allowed to equal 0. So this is where we would have our NPVs. So we would say that X is not allowed to equal these certain values. Or it could be that we have a radical function. So the square root of f of x. And in this case, we have to make sure that f of x is greater than or equal to 0. So you always want to determine that domain first, because it's going to help narrow your vision of scope. You're not going to be looking at all real numbers if your domain only goes from 1 to infinity. All right. Then we're going to find our intercepts. So the x-intercepts make y equal 0. The y-intercepts make x equal 0. We want to check for symmetry. So subbing in that negative x to see if it pops out our original function or the negative of the function. Because if I know I'm symmetric about the y-axis, if I know the left half, I know the right half. Again, I only have to do half the work. If it's odd, then I know I'm symmetric about the origin. So if I know the bottom left, I know the top right. So again, half the work. Once we've done those, then we kind of actually start into the calculus of it, and we identify our asymptotes. So vertical asymptote, we're going to set the denominator of rational functions to 0 and solve for x. If x equals a is a vertical asymptote, then we're going to check the behavior of the left and the right. Which one's going to infinity, which one's going to negative infinity. For horizontal, we want to make x go to infinity and see if our graph either also approaches infinity or if we approach a specific value and we have that horizontal asymptote. Then again, first derivative now. So this is the limits. Step D, we're using limits to find our asymptotes. For E specifically, this part specifically, we need the first derivative. For local extrema, you could do the first derivative test or the second derivative test. That one is up to you. For concavity, we have to use the second derivative. And then we put all of that together and we sketch the curve. So first drawing in our vertical horizontal asymptotes, plotting your intercepts, your local max, local min, inflection points, and then connecting these with nice smooth curves. No V's, no straight lines, nice smooth curves. Okay, so let's try this out and see how it goes. All right, so part A. And you guys don't have to scroll back and forth. Remember, this is written on the whiteboard. So we want to find our domain. Well, this is just a polynomial function. For a polynomial function, our domain is all real numbers. Okay, so B wants us to find our intercepts. Remember, for x int, we're going to do 0 equals, and we're going to factor this. Looks like I can pull out an x cubed. This is going to leave me with 3x squared minus 5. So our x-intercepts are going to be 0 and the square root, positive or negative, of 5/3. So remember, we're just setting this equal to 0. So 3x squared equals 5, x squared equals 5/3, and square root both sides to get the positive or negative square root of 5/3. All right. We're going to do y-int. So we're going to make x equal 0. Well, that's easy. It's just 0. All right, and again, I like to plot these points as soon as I get them. So I know I have a point here at 0, 0. I know I have a point here at negative the square root of 5/3. And I have a point equidistant on the other side that's the square root of 5/3. All right. C is our symmetry. So we're going to sub in f of negative x. So this is going to be 3 negative x to the 5 minus 5 negative x to the 3, which is going to be negative 3x to the 5 plus 5x to the 3, which, if you look at this, it's just negative 3x to the 5 minus 5x to the 3, which is negative f of x. So this is an odd function. So we're symmetrical about our origin, the point 0, 0. So whatever happens before this point here has to happen the exact same after that point. All right, part D, our asymptotes. All right, so remember, vertical asymptotes happen when we have rational functions. A polynomial, again, because we have a domain is all real numbers, I have no asymptotes. So vertical asymptotes, there are none. So we're going to look for horizontal asymptotes. We're going to see what happens when our function goes to infinity. So we're going to do the limit as x approaches infinity. We're going to do the factored form. So we're going to have x cubed 3x squared minus 5. Well, I'm going to have a large positive number times by a large positive number. So that's going to go to infinity. So no horizontal asymptote on that side. negative infinity of x cubed, 3x squared minus 5. Well, a negative cubed, that's going to be a large negative. This is going to be a large positive. So this side is going to go to negative infinity. So it looks like on the other side, as I'm approaching here, I'm going to go down to infinity, which makes sense because we have to be symmetrical about this origin. So if I'm up on this side, I have to be symmetrical on this side, so I have to go down. All right. E is our intervals of increase and decrease. Intervals of increase and decrease means I need my first derivative, which is going to be 15x to the 4 minus 15x squared. So I can pull out a 15x squared. It's going to leave me with x squared minus 1. So my critical values are x equals 0 and positive, negative 1. All right, so let's find my areas of increase and decrease. So we're going to have x squared. You can do the difference of squares here. Have x plus 1, x minus 1, which is going to tell me something about my derivative. All right. Doing to doing, doing to doing, doing to doing. Right, so negative 1, 0, 1. So if I put negative 10, negative 0.5, positive 0.5, and 10. Well, this doesn't matter, always positive. Negative 10 plus 1, that's going to be negative, positive, positive, positive. Negative minus a negative, negative, negative minus a negative, negative, smaller minus a negative, negative, and bigger, that's going to be my positive. All right. So we get positive, negative, negative. This is going to be positive, negative, negative, positive. All right, so you can see I only have local maximums in this one. Sorry, one local maximum, one local minimum. So I have a local max at f at negative 1. Well, that's going to be negative 3 plus 5, so that's going to be 2. And we're going to have a local min at f at 1. Well, 3 minus 5, that's going to equal negative 2. So at negative 1 and 2, I'm going to have a local max. And at 1 and negative 2, I'm going to have a local min. So again, you can kind of see that symmetry happening that we know has to happen because we have an odd function. All right, so this was part F here, finding our local max and min. All right, G is our concavity, which means I need my second derivative. So 15 times 4, we're going to have 60x cubed minus 30x. So we're going to put out a 30x. It's going to leave me with 2x squared minus 1. All right, so for my concavity, Again, when I set this one equal to 0, I'm going to have negative the square root of 1/2, or 1 over the root 2, depends on how you want to write it, 0, and so this is the other way you can write it, just because the square root of 1 is 1. Okay, so I have x, and I have 2x squared minus 1. Alright. So, again, we can kind of pick random numbers. Root 10, root 1/4, negative, negative, root 1/4, and root 10. So this one's not going to matter. Negative, negative, positive, positive. So again, I kind of picked my test points to be roots, because the square root of 10 is squared is 10, so 20 minus 1, that's going to be positive. Well, 2 times 1/4 is 1/2. 1/2 minus 1, that's going to be negative. 1/2 minus 1 is going to be negative. And this one's going to be positive. So we're negative, positive, negative, positive. So I'm concave down, concave up, concave down, concave up. Which means I have inflection points that occur when x equals 0 and when x equals positive or negative 1 over the square root of 2. Alright, so let's sketch this all together. So I'm going to have an inflection point in here, and I'm going to have an inflection point in here. So you can see I made my graph a little too smooshy. So I should have moved my x-intercepts out a little bit more when I first sketched them. That is kind of one downfall of putting the points in first, but you could always erase and replot if you wanted to. I'm too lazy right now. Alright, so I am increasing until I hit -1, and I am concave down until that point. So I'm concave down, and I'm increasing to that point. So concave down, and I'm through my x-intercept, reaching that point. Still concave down. Then I switch to concave up. So at this inflection point, I switch to concave up. I stay to concave up until I hit 0, 0, my other inflection point. Switch to concave down till I hit that next inflection point. Back to concave up. Then I start increasing again. So you can see I have that symmetry about the origin. Again, my graph's a little too smooshy, but you can see I'm concave down, switch to up, switch to down, back up to up. And there we have it. There's our curve sketching. You can find the exact value of y if you wish by putting this back into our original function. But for this one, we didn't have to worry about that one too much. Alright, so I'm actually going to leave the examples there because I think that's enough information for today. For if there's still time left in class, because you do have the homework from the last one to work on, and the only one I want you to do from this one right now is this guy here. And we'll worry about these square roots and cube roots and all of those other ones for Thursday.